Is this compound polar? How about this one? Well, comment your answer down below and I'm going to explain it now. So welcome to Monroe Tutoring. This is the lesson on molecular polarity. So this is building on my last lesson about bond polarity. And then before that, we did electronegativity along with the other periodic trends. And then if we go way back, molecular geometry is also critical to this. So if you haven't seen those lessons, check them out, but I'm going to summarize them all in this lesson anyways, okay? So before we jump into these two examples, let's start off with a simpler one, okay? Let's do something like HCl. And so if you look at hydrogen and chlorine, we know that chlorine is more electronegative than hydrogen. Remember that the trend in general is up and to the right. Chlorine is much further to the right than hydrogen, so it has a much higher electronegativity. And remember that electronegativity is essentially a measure of how strongly an element attracts electrons in a chemical bond. And so what that means is the chlorine is going to attract the electrons much more strongly than the hydrogen. And so in my last video on bond polarity, I showed you guys that we're going to draw a dipole moment, and we can draw it directly on the bond itself, indicating which way the electrons are residing in more. So we're going to point towards the chlorine because it's more electronegative, and that shows that this side of the molecule, or at least this side of the bond, is going to be more electron rich, and that this side is going to be more electron deficient. And so we're pointing towards where the electrons are spending more time. And this little tail that kind of looks like a plus, it's showing the region that's more partially positive, okay? Now, if we take a look at the electron cloud now, like I said, this has to be more electron rich. So if we have this big electron cloud here, and the electrons are spending less time on this side, so it's going to be something like this, right? And so that means that the right side that has the excess of electrons, they're spending more time on that side of the molecule, is going to be partially negative. So I'm going to put a couple minuses over there. And then this side that has the deficiency of electrons is going to be partially positive. So I'll draw a couple little pluses on this side. And then just like a magnet has a north pole and a south pole, right? So if we have a magnet and we have the north pole and the south pole, well, if we had another magnet and we had the orientation like this, where the south is over here, the north is over this way, well, there's going to be an attraction from the north side of one to the south side of the other. And so this magnet has two poles. Well, it's going to be the same thing with the molecules. Because we have a positive side and a negative side within a molecule, it's going to behave just like a magnet would. And so we call it polar. So if I had another HCl and it was aligned to just like I have the magnets, the positive side of this magnet is going to be attracted to the negative side of the other. And I meant to say molecule, not magnet. I think you guys get the point. Now, I'm going to expand on that topic in my next video on intermolecular forces. But for now, let's just keep it with molecular polarity. So in this molecule, we have a net dipole because there's only one dipole moment. Nothing's canceling it out. So the net dipole means that it's a polar molecule. So let's look at these examples now. If we take a look at this boron trifluoride, we know that the fluorines are more electronegative than the boron. And again, if you look at our periodic table, fluorine's here, boron is there. So to the right is going to be more electronegative. And so if we draw the bond dipoles, we're going to be pointing towards the fluorines, which means that the electrons in the bond are more attracted to the fluorine than they are to the boron. And that's going to be, of course, true for the other two fluorines. And by the way, I'm not drawing the lone pairs on the terminal atoms here. Only the lone pairs on the central atom really matter for this lesson, okay? So we can just assume that all of these elements out here have octet, but we don't want to make this too busy, okay? So the point is, this now has the bond dipole moments. And we want to see what is the net dipole to see if the molecule is going to be polar or nonpolar. And so if we look at it, the way that we drew it, it looks like this dipole moment and this one cancel each other out, right? Because they're pointing in opposite directions. And that we have this net dipole pulling down over here. So it looks as though this would be a polar molecule, but this is where molecular geometry is critical. So if you know the molecular geometry from that lesson, we have 1, 2, 3 electron regions on the central atom and no lone pairs. So that means the electron geometry is trigonal planar, and so is the molecular geometry. And so trigonal planar geometry looks more like this. If I take my boron and I put the 3 fluorines and they are all spread out more symmetrically, we have this 120-degree angle between each of the terminal atoms. And then if we draw our bond dipole moments, we can see that due to this symmetry, and it's trigonal planar, meaning it truly is flat like it is on the board, these dipole moments are going to cancel each other out. And so the idea is, if you had 3 guys and you tied 3 ropes to some center point, and the guys are all the exact same strength, is that not going to move one way or the other? And the answer is no. If they all have the same strength and they're all pulling in this symmetrical fashion, it's all going to cancel out, and there's not going to be any winner in this 3-way tug of war, right? So that means that this molecule is non-polar. So we have polar covalent bonds because the sharing of the electrons in the bonds is unequal. And the electrons are going to be pulled towards the more electronegative elements. So the electrons are going to be kind of crowded towards the fluorines. But due to the fact that it's evenly distributed like this, not one side of the molecule has an excess and the other side deficiency in electrons. It's just going to, the electron cloud is symmetrical. So in other words, we have some sort of electron density around this fluorine, the same electron density around that one, and of course the boron is going to be kind of deficient. But the point is, it's not like one side is partially positive and the other side is partially negative. The outside of the molecule is going to have a little bit of a negative, and the inside area is going to be a little bit positive. These are not formal charges. These are just my little diagram of little partial charges, okay? The point is, this is symmetrical. So if you had 2 of these molecules, it's not like you're going to have, a positive here attracted to the negative here. The outer realms of this molecule are all partially negative. So that makes it non-polar. There's not poles like in a magnet where you have the north and the south, or there's going to be a plus and a minus. It's just symmetrical. So that's a non-polar molecule. So now let's look at the other example. If we take a look at this one, and let me just get rid of this now. If we take a look at this one and we draw our bond dipole moments, well, we know that chlorine is more electronegative than carbon, and chlorine is over here, carbon's over there, and so it's going to be more electronegative. You can also just look at an electronegativity table. So let's draw our bond dipole moments going like this. And then carbon is a little more electronegative than hydrogen, so these ones are going to face inwards actually. And now if we look at it again on paper, it looks like this dipole moment and this one are going to cancel each other out. And then this one and this one are going to cancel each other out. But our molecular geometry is key here. So if we take a look at what this molecule truly looks like in reality, a tetrahedron, this is the shape of a tetrahedral molecule. And so if the green ones are the chlorines and the white ones are the hydrogens, I can kind of make it look like this on paper, where the chlorines are in our horizontal plane and the hydrogens are in the vertical plane. I can even flip it around like this. But if we look at it in 3 dimensions, there is a realm of the molecule, one side of it, this side over here, where the hydrogens are, that's going to be partially positive, and this side over here is going to be partially negative. So this side's a little bit positive, where my hand is now. This side is partially negative, where my hand is now. So that makes a polar molecule. And we actually can draw it on paper, because of course we could have just switched where the chlorine and the hydrogen were, and then we could have redrawn this like this, right? So we could have had chlorine, this could have been a hydrogen, this could have been a chlorine and hydrogen, and now this is the exact same molecule. There is no difference here. It's just a different way of drawing the Lewis structure. Now it's a little more obvious that, oh yeah, we're going to have this partial negative on this side and partial positives on this side. And so this region of the molecule is deficient in electrons. This region of the molecule has an excess of electrons. And so if we had another of the same molecule float over, you would get that polarity, right? Or it is polar, but I mean, it would align like magnets do, with like the positive side of this molecule would be attracted to the negative side of the next molecule over, right? Again, I'm going to talk about the intermolecular forces more in my next lesson, but the point is you need to understand molecular geometry to tell if a molecule is polar or nonpolar. And by the way, just to kind of prove the point, where if I hold this like this, it looks like I have it on the page, right? Where the hydrogens are in the vertical plane, the chlorines are in the horizontal, or I could have done it like this, but I can also flip it to have the chlorines over here, where one's coming this way and the other one's going down, and then the hydrogens are kind of towards the top right. So just kind of showing you that these structures, although drawn differently, are the same molecule, right? If I take a hydrogen out from here and I flip it with a chlorine, I'm not going to get a different molecule. I'm just going to get the exact same thing, and I can just flip it around to make it back to what it was in the first place. All right, guys? So let's just look at another example, I suppose. And as I'm thinking of what to draw here, guys, if these lessons help you, please give a like, follow, share this with someone that could use the help, save it so you can review again later. And if you'd really like to support the channel, you can check me out over here and patronize me. That helps me to continue making these videos for free. So now let's look at another example. Let's do carbon dioxide. This is a classic. And let's actually do two more. Let's do carbon dioxide and let's do water, okay? So if you look at carbon dioxide, of course, you need to know how to do Lewis structures. I have a lesson on that. And so if I draw these two molecules, these are asked all the time on exams. So if you just get good at drawing these molecules, you're just going to kind of remember them. But I want you to understand why they are polar or nonpolar. And so if we look at carbon dioxide, this central atom has only 2 electron regions. There's no lone pairs, so this is a linear molecular geometry. And although the dipole moments are going to go towards the oxygens here, since it's linear and it's symmetrical, they cancel each other out. Pulling to the left, pulling to the right, that is a net dipole moment of 0. There is no net dipole moment. And so that means that this is a nonpolar molecule. Again, we're going to have kind of an electron-rich region on the exterior of this, and the interior is going to be a little bit electron deficient, but it's not that one side of the molecule is positive and the other side's negative. It's symmetrical, so it's a nonpolar molecule, even though the bonds in it are polar bonds. And then over here, again, hydrogen and oxygen, oxygen's more electronegative, so the bonds are going to be polar, but let's see if the molecule is. Well, oxygen's more electronegative, so the dipole moment is going to go towards the oxygen. And now this looks linear the way that we draw the Lewis structure, but we need to know the molecular geometry. There's 1, 2, 3, 4 electron regions, right? Each lone pair on the central atom or atom bonded to the central atom is an electron region. So 4 electron regions gives us tetrahedral. And so that's kind of this shape, but 2 of the electron regions are not atoms, they are just lone pairs. So if you just kind of take a tetrahedral molecule and just pull out 2 of the atoms, this is now our new shape, and that's bent. So water does not have the same geometry as CO2. Water is going to look more like this. We have our oxygen, and then our hydrogens are going to be over here, and we have our lone pairs like this. So now if we redraw these bond dipole moments, we can see that they do not cancel. We have a net dipole that's going to be facing this direction, right? Our net dipole is going to be like this, right? And so that means that this side of the molecule is going to be partially negative, and this side of the molecule is going to be partially positive. And that means that we have a polar molecule. So that's polar covalent bonds and a polar molecule. This one has polar covalent bonds and a nonpolar molecule because the dipole moments cancel. And then just for our kind of final thing as a send-off, if we have something like fluorine bonded to fluorine, And for some reason, I'll draw the lone pairs this time. Well, this is the same element. So it has the same electronegativity, so there's no dipole moment at all in the first place. So this bond is nonpolar covalent, and then so there's just no arrows to draw one way or the other. So of course, then that molecule is also going to be nonpolar. All right, guys. So again, if this helped, please give a like, follow, share, save. To review it again, share it with a friend. Check me out over here, and I'll see you guys in the next one.